Hello everybody. In this video, we're going to discuss molecular polarity, which is the last topic of chapter 5. This topic is based on the first three topics of chapter 5, okay? So you do have to have a good understanding of these topics before you watch this video. Let's take a look at this slide. Before we discuss molecular polarity, I do want to review bond polarity. Bond polarity and molecular polarity, these are related, but they are different. Okay, so you will see the difference in a moment. But when we discuss bond polarity in the first topic of this chapter 5, we talked about how we use electronegativity difference to decide whether a bond is just nonpolar covalent bond, polar covalent bond, or ionic bond. Let me give you some example, okay? So if you are talking about chlorine, let me write that again, chlorine bond, because the delta En, delta En of this bond is 0. Why is that? Because the two chlorine, they have the same electronegativity difference between the two atoms would be 0, naturally. And the electrons between the two chlorine atoms are shared by these two chlorine atoms equally. So there is no positive end or negative end on this molecule. All of the electrons distribute on the surface of this molecule evenly. Okay, so it's a nonpolar bond. Nonpolar bond. And the polar covalent bond, let's see HF, okay? Hydrogen fluoride, because the electronegativity difference of these two atoms is between 0.4 and 2.0 window. Therefore, it's a polar molecule. It's a polar bond, okay? Polar bond. We are going to focus on the bond only. And what does it mean by polar bond? That means that this bond, one side is negatively charged, the other side is positively charged. So when you see hydrogen and fluoride, because fluorine has much higher electronegativity than hydrogen, fluorine grabs those two electrons toward itself. Okay, so the fluorine, most of the time, those two electrons will move around the fluorine. And occasionally, these two electrons will move around the hydrogen, but not that very often. Because of this difference, hydrogen side would be positively charged, and the fluorine side would be negatively charged. So we said that this bond is a polar bond. It has a positive end and negative end. Therefore, we have this polar bond, and when we label the polar bond, we usually use a large arrow with a cross at the end to indicate the bond polarity of a molecule. And how do you remember the labeling of this? You know, this one looks like a positive sign, right? So you go from positive side to the negative side when you label the polarity of a bond. And we have a dipole moment. Remember, we said that dipole moment of this molecule is not 0. This bond is polar. All right, now ionic bond, for instance, sodium chloride. Well, because of the electronegativity difference between the two atoms is larger than 2.0, okay, sodium will lose electron to chlorine, so they are not sharing electrons. Instead, they are gonna just electron transition from metal to non-metal, and between the two, it's just gonna be the pure electrostatic interaction. So it's ionic bond. Okay, so let me write it here. Ionic bond. Okay, why do we need to discuss this bond polarity before we talk about molecular polarity? Well, here you probably noticed that, okay, so if the molecule has just only one bond, then the bond polarity is the molecular polarity. Hydrogen fluoride is one example. Hydrogen chloride is another example. Well, hydrogen chloride electronegativity difference is between this window, therefore this bond is polar bond. Because this molecule has only one bond, then the bond polarity is the molecular polarity. Okay, go from the positive go from hydrogen side to the chlorine side. And this is the electron density map. As you notice that this side is smaller than this side. So, and the color is different. This one is a little bit blue and this one is yellowish, okay? That tells us this side is negatively charged and this side is positively charged, okay? So this is one first situation. If the molecule has only one bond, then the bond polarity is the molecular polarity, okay? All right, and same thing here. If this bond is nonpolar, then the molecule itself is nonpolar. Now let's see the second situation. You have carbon dioxide. Well, we know that you have two CO double bond. Well, for each CO double bond, delta En is between 0.4 and 2.0 window. Therefore, for CO double bond itself, it's polar. You can see that because carbon has less electron negativity than oxygen, the carbon, if you are talking about the CO double bond, then the carbon would be partially positive, right? And oxygen would be partially negative in this case, when you compare these two only. On the other side, the oxygen and the carbon, another CO double bond, you have the polar bond again. And the dipole moment, can you see the polarity? The labeling is the opposite, the going from your left side to right side in this case, okay? All right, now how about the molecular polarity in this case? You have two polar bonds, but how do you figure out the molecular polarity? Well, you have to do Victor addition. Victor addition to figure out whether a molecule is polar or nonpolar, okay? If this molecule has more than one bond. For this carbon dioxide molecule, these two Victor, dipole moment, Victor, if you add them together, because they are opposite, they are pointing to the opposite direction and they have the same strength, the polarity of the two bonds are identical. Therefore, when you add these two Victors together, then you cancel, they are going to cancel each other out. In other words, the Victor addition tells you that the whole molecule would be nonpolar. The polarity of the two bonds cancel each other out. Therefore, the whole molecule would be nonpolar. Okay, so now you can sense the difference between the molecular polarity and bond polarity. Bond polarity does not represent the molecular polarity if you have more than one bond in the molecule. Okay, I hope you remember this. All right, now let's take a look at the water, the third example. Water OH bond is polar. You have two OH bond. Now, how about the molecular polarity? Now, Victor addition. You have one Victor here, another one Victor here. Now, you add them together right here, okay? Right here. Remember, when you do Victor addition, those two Victors will have to start from the same point, okay? So in other words, this Victor comes from this one here. This Victor comes from this one, okay? I just shifted them a little bit to let them start from the same spot. Now, when you do Victor addition, okay, like this, then you have to do this kind of drawing. Okay, you draw a dashed line, this one here, that is parallel to this Victor with the same length, and you draw another dashed line that is parallel to this Victor with the same length. And then what will happen here is the sum of this Victor addition will generate a new Victor that will be start from this point here and to the crossing point of those two dashed line. Okay, so this is I'll use the red color. Okay, I'll use the red color to label it. So the overall or the net vector, the net dipole moment of this molecule will be from this point to this point. Okay, so as you can see that these two vectors, they cannot be cancelled by each other. Therefore, you have a net dipole moment in this case. So that tells us that this molecule is polar. And here on this density map, you can see that oxygen side is red. And because the oxygen has a higher electron negativity, it's the ending point of this red arrow. Therefore, it's negatively charged. On this hydrogen side, because both hydrogens have less electron negativity than oxygen, they have less electron density than oxygen side. Therefore, this side would be positively charged. Okay. Now, as you can see, the vector addition, it could be a hassle, right? Because you do have to add them together, and this is just two bonds. If you have multiple bonds, like 5, 6 bonds, then the vector addition could be a very a big trouble. Okay, it could cost you a lot of time to figure it out. So is there a easier way for us to figure out whether a molecule is polar or nonpolar? The answer is yes. Okay, but don't get me wrong, the vector addition is the ultimate and the most accurate way to figure out whether a molecule is polar or nonpolar. But we do have a flow chart for you to follow in Chem 1 or Chem 2. So I believe that this flow chart will help you, figure out the molecular polarity easier and faster. And the flow chart is not perfect, but it's good enough, okay, for most of the molecules in our college chemistry. Okay, let's take a look at the flow chart. Here is the flow chart. Okay, so essentially you just keep asking you questions. The first question, are all electron groups of the central atoms identical? Remember, electron groups means either the bonding chemical bonds or long pairs. Okay, are all electron groups of the central atoms identical? If the answer is yes, then it's nonpolar. If the question is no, you ask yourself another question. Is the molecular geometry linear or square planar? If the answer is yes, then the molecular would be nonpolar. If the answer is no, that's going to be polar. Okay, so as you notice that in order to answer those questions, you do have to have the Lewis structures available. You do have to figure out the molecular geometry first. Okay, so that's why I said that this topic is based on the previous 3 topics of this chapter. Let's use the examples to demonstrate. I drew those Lewis structures and the geometries for these molecules already in order to save your time. So we're just going to use those charts, okay? Focus on this chart. First molecule, CH4. This is the tetrahedral geometry, and you can see the dashed wedge and solid wedge. Now, let's ask ourselves the first question. Are all electron groups of the central atom identical? Central carbon, 4 single bonds, 4 CH single bonds. Therefore, these 4 bonds are identical. This is a nonpolar molecule. The answer is yes. So it's a nonpolar molecule. Let me label it. Nonpolar molecule. Okay. CO2, well, we know that this molecule is nonpolar already from the previous slide, but let's use this chart and just confirm. Lewis structure. Okay. First question, are all electron groups of the central carbon identical? You have two identical CO double bonds. They are identical, so answer is yes. It's nonpolar. Okay, it's nonpolar. All right, now let's see the next one. IF5. This is a geometry of this molecule. First question, are all electron groups of the central atom identical? Well, you have iodide as a central atom, and it has 5 IF single bond, and it has a lone pair. And we know that the IF single bond is different from the lone pair. So the answer for the first question of this molecule is no, because you have a lone pair, you have single bond. They are not identical. Okay, so the answer is no. Let's ask ourselves the second question. Is the molecular geometry linear or molecular planar? Well, if you use the whisper theory, you will figure out the molecular geometry of this molecule as a square pyramidal geometry. Okay, square pyramidal geometry. So the answer for this question of this molecule is no. So this is going to be a polar molecule. Polar molecule. Okay, so this is how we use this chart to help us figure out whether a molecule is polar or nonpolar. Let's see more examples. First one, the nitrate, an O3 minus, and this is the loose structure of this molecule. As you can see, the geometry is trigonal planar geometry. Are all electron groups, Are all electron groups of the central nitrogen identical? Well, here's the thing. For this particular structure, it looks like you have double bond here, single bond here. So it looks like they are different. However, if you remember what we did for resonance structure, that topic, we said that this double bond can migrate. Okay, it doesn't matter which oxygen share the lone pair if you haven't remembered the previous videos. Okay, so that means that 3 bonds are identical. Okay, so the answer for the first question of this NO3 minus species is yes, they are identical. So it's nonpolar. Nonpolar. And I do want to remind you about one thing. That is the polarity of a molecule and the charge. Well, no doubt about that this anion is charged, okay, but it's nonpolar. It just sounds like a little bit confusing. But the polar is about how the electrons distribute on the surface of the molecule. Okay, the charge is about the overall property of this molecule. So even if this NO3 anion is charged, but this charge or this extra electron is evenly distributed on the surface of this NO3 ion, therefore it's nonpolar. Okay, it's charged, but the charge is evenly distributed on the surface, therefore it's nonpolar. I hope you understand this. Okay, we'll do more practice. Now the next one, xenon tetrafluoride. All right, first question, are all electron groups are identical? Well, you have 2 lone pairs, 4 xenon fluoride bonds. Therefore, those 6 groups are not identical. The answer is no. Now, next question, is the molecular geometry linear or square planar? Well, when you look at this, the geometry is a square planar geometry. Okay, again, from the whisper theory, square planar geometry. Therefore, the answer for the second question is yes. So this one is going to be nonpolar. Nonpolar. And if you are talking about the Victor addition, this one is easy because xenon fluoride, this bond is going to be polar, this bond is going to be polar, but they have the opposite dipole moment. Therefore, these 2 bonds, they cancel each other out. These 2 bonds, they are going to cancel each other out. And these 2 lone pairs, they are going to cancel each other out. Therefore, the whole molecule is nonpolar. All right, the last one here in this topic, CHCl3, chloroform. Well, you have geometry like this. First question, are all electron groups of the central atom identical? Well, if you look at this, you have CH bond, CCl bond, and CCl bond, and CCl bond. Well, the first look, it will tell you, okay, all 4 of them are single bonds. So they are identical. But be careful about the atoms. Okay, CH bond itself, it has a different electron negativity difference from the other three. So the bond polarity of this bond is different from the other three. Okay, so even if all four of them are single bond, but because of the different electron negativity difference of those bonds, these four, at least this one, is different from others. Okay, so the answer for the first question is no. Now the second question is the molecular geometry linear or square planar? Of course, this geometry, we know it, it's tetrahedral geometry. So the answer for this one is no. Therefore, this is going to be a polar molecule. Polar molecule. All right. Okay, good. We'll do more practice in class, and if you have any questions, you let me know.